Hi gang. Today I want to talk about Taylor's theorem, which is a theorem that you learned in calculus, but it's so fundamental to doing numerical analysis, to estimating errors in numerical calculations, that it's worth actually proving it from scratch right now, just to make it clear in your own mind how it works. It's actually not a difficult theorem, but it's terribly important. So first what I'm going to talk about is what I call bootstrapping a function. Bootstrapping is when you start out from nothing and pull yourself up by your bootstraps, and I'm going to talk about how a function could do that, meaning a function that starts off at 0, how big can it get? That's the basic idea. So first of all, just recall from the fundamental theorem of calculus, you know that if you integrate the derivative of a function from a to b, that is a differentiable function, then what you get is the difference between f of b and f of a, right? F of b minus f of a. If you rearrange this slightly, solve for f of b in this equation, then you get this expression, right? So f of b equals the value at a, f of a, plus the integral of f prime from a to b. Okay? Now, as I said, we want to talk about bootstrapping a function, so a function that starts off from 0, from nothing. So we're going to assume that f of a is 0, and therefore that this term is absent, right? That term is 0. And furthermore, let's assume that we know what the max and min of f prime are on the interval. So I'm going to let little m and big M be the min and max, respectively, of f prime on the interval. So when you integrate this expression, f prime, the smallest integrand, the smallest the integrand can be is little m, and the biggest it can be is big M. So we get this inequality, right? That the complete integral, which represents the value of f at the point b, the smallest it could be is m times the length of the interval b minus a, right? The length of the length of the interval over which we're integrating. And the biggest it could be is capital M times b minus a, right? That's perfectly simple. Furthermore, notice that b is basically arbitrary here, right? The value of b could be any point on really on the interval in which f is differentiable, just as long as it's differentiable on the entire interval from a to b, but b could be any point. So what I'm going to do is I'm going to rewrite this slightly, and I'm going to say we can think of it this way. We can say that f of x, right, the value of f of x at any point is between little m times x minus a and big M times x minus a, right? And of course, these are just linear functions, right? And so here's the picture of that inequality. The blue line is supposed to be the actual curve, y equals f of x. The biggest slope that f takes, the maximum of f prime, kind of attained here, right? The biggest slope is there. The smallest slope is a negative slope at the beginning. And if you were to extend the negative slope continuously, you'd get the lower orange line. If you were to extend the maximum slope at the end continuously, you'd get the upper orange line, right? So the actual curve, y equals f of x, lies between the straight line with the minimal slope and the straight line with the maximal slope, right? This is all perfectly simple so far. Now, to make the bootstrapping more interesting, let's assume that we have a function which is not only 0 at a, but also its derivative is 0 at a. So think of the green curve in this graph here, right? So it's 0 at the point A over here, and also its derivative is 0, so it starts out with a horizontal slope, right? And then, because it starts off with a horizontal slope, initially it's not changing very much, so that's going to put further restrictions on how quickly the value can grow over time. So now we can work off our previous result. What I'll do is I'll assume that the derivative of g is just equal to the f that we were just looking at, right? Because g prime, as I said, we'll assume that g prime is 0 at the point A. And so it's just like the function f we were looking at previously. And then since in addition we're assuming g of a is equal to 0, then we have this identity that g of b is equal to the integral from a to b of g prime. And of course we're assuming g prime is equal to f, so it's just equal to the integral from a to b of f. Now, making use of the inequality we had on f, right, that we saw previously that f of x is bounded by little m times x minus a and big M times x minus a. That means we get a bound for this integral, right, which means we get a bound for g of b. So g of b has to be between, on the lower side, it has to be at least as big as the integral from a to b of little m times x minus a, and no bigger than the integral from a to b of big M times x minus a. Now, these integrals are easy to do, because the m's are constants, so this is just a first-degree polynomial that we're integrating. Very easy to integrate this. The integral becomes m times b minus a squared over 2, right? And so on the left side, the lower side g is bounded by b minus a squared over 2 times m, and on the upper side by big M times b minus a squared over 2, right? Now, making the same result, it's just disappeared. Oh, there it goes. Okay. Making the same argument we made before, this is actually valid for any value of b on the interval where g is differentiable. So we can restate it like this. We did it again. We can restate it like this. We can say that g of x is always between m times x minus a squared over 2 and big M times x minus a squared over 2. Okay, and so this is a parabola. This is describing a parabola. In this case, if m is negative, this would be a parabola that opens down. So that would be, that would be this lower orange parabola. And the one on this side, if you're assuming that big M is positive, then this would be a parabola that opens up. So what we can say is that the green curve, representing g, is between the lower parabola and the upper parabola, right? So it seems like we can keep extending this trick, right? We can keep extending it to functions for whom more derivatives are equal to 0. So we could do it, for example, for a function h, which is equal to 0 at a, and also its first and second derivatives are equal to 0 at a. In that situation, h prime would satisfy exactly the same conditions that g did, the g from our previous slide, right? That h prime would be 0 at a, and its derivative would be 0 at a. Therefore, we would have the same inequalities for h prime of x that we had for g previously, right? H prime of x would have to be greater than or equal to little m times x minus a squared over 2 and less than or equal to big M times x minus a squared over 2. And therefore h, which would be the integral of h prime, will be between these two integrals. Once again, we can easily integrate these because they're just polynomials, and the m's are constants. So in this case, we get a cubic polynomial. Now, and we pick up, by the way, an extra factor of 3 now in the denominator. 3 times the 2 that was there previously gives us 3 factorial, right? 3 times 2 times 1. Okay, so it seems that we can keep doing this, right? We can keep doing this for functions that have more and more derivatives which are equal to 0. And so this leads to what I call the bootstrapping theorem. Now that's not actually a standard term in the subject. So if you refer to the bootstrapping theorem, I'm afraid no one will know what you're talking about. But I find it a convenient way to refer to this. So using this idea that a bootstrapping function is one for which all of its zeros and its initial values start off at 0. And that makes it very difficult for the function to grow, right? Because if its value and all the derivatives are 0. Let me just point out there's a very useful notation here. when we write f raised to the superscript parenthesis n, that represents the nth derivative of f, right? So if you want to talk about higher order derivatives, this is a more convenient way to do it than to keep writing primes, right? Prime, 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 or something. And also by convention, when we use 0 for n, f to the parenthesis 0, that's just the original function f. So it's like the 0th derivative of f is just f itself. Okay? So now, the bootstrapping theorem, so-called, says that if f is a continuously differentiable function, differentiable n plus 1 times on the interval from a to b, and f and its first n derivatives are 0 at a, at that left endpoint, then we get this bound on the values of f of x for any x in the interval. F of x is, it's bounded on the one side by little m, where little m is the minimum value of the n plus first derivative of f on the interval. So little m times x minus a to the n plus 1 over n plus 1 factorial, right? Simple generalization of this. And on the other side, it's less than or equal to capital M times the same expression, capital M being the maximum of the n plus first derivative on the interval. There's an alternative formulation for this, which is sometimes useful. Actually, and it's the formulation you will usually see in textbooks, right? So let me explain this. Because f of x is between little m times this fraction and big M times the same fraction, then intuitively it's pretty obvious there must be some mx, let's call it, between little m and big M for which you have exact equality. That is, f of x would be exactly equal to this intermediate value of m times the same fraction, right? So there's got to be some intermediate value m sub x between little m and big M for which this would be exactly equal. Now, furthermore, because the n plus first derivative of f is a continuous function, and it's a continuous function which takes a small value little m and a large value big M, and because it's continuous, it must also take all values in between. So the n plus first derivative of f takes all the values from little m to big M and everything in between, and therefore there must be some point where it takes the value m sub x, right? So what we can say is there must be some point, I'll call it c sub x, on this interval between a and x, where the n plus first derivative of f is exactly equal to m sub x. Now, plugging this in, substituting this value for mx into this expression and rearranging things slightly, I get this. So we can say that f of x is exactly equal to the n plus first derivative evaluated at some point cx between a and x, and then divided by n plus 1 factorial, right, as before, and times x minus a to the n plus 1. One reason for writing it this way is because you isolate this polynomial x minus a to the n plus 1 by itself over here. One advantage of this formulation, rather than using inequalities, writing it as this exact equality, but in terms of this rather undetermined point cx. We don't exactly know where cx is, right? So this isn't, in a sense, it's not such a useful formula because we don't know what cx is, right? Whereas we can know what little m and big M are by calculating the derivative and finding the max and min. But one reason that this formulation is useful is that we can also use this same formulation when x is less than a. Up until this point, I've been assuming that x and the point b are to the right of a, right? That we're looking at an interval with a as the left endpoint and b as the right endpoint, and x could be any point in between. But same formulation that I have here works just as well when x is a point to the left of a, so if x is less than a, right? As long as the same differentiability condition holds, right? That it's differentiable, f is n plus 1 times continuously differentiable on the interval. In this case, the interval would be from x on the left to a, and also that, the derivatives are 0 at a. You can also write a formulation in this form when x is to the left, but then you have to reverse some of the signs, and it's just a little confusing. So it's a little bit easier to think of it this way, because the same formulation works for points x which are either less than a or greater than a. So now we can do Taylor's theorem. The idea of Taylor's theorem is that it shows how well you can approximate a differentiable function using a polynomial. Okay, so suppose f is a continuously differentiable function, continuously differentiable n plus 1 times, on some open interval containing the point a, right? So it's differentiable n plus 1 times in the neighborhood of this point a. And we'll define a polynomial p that we will use to approximate f. And p is defined in terms of powers of x minus a. So it's got a constant term, and it's got a first power term of x minus a and a second power term, x minus a squared, and so on, right? And we're going to make it an nth degree polynomial, one less than the number of derivatives that f has, right? So it'll go up to x minus a to the n. And then each one of these terms is going to have a coefficient, and there's also going to be a constant coefficient. And all the coefficients will be determined by the derivatives of f. So the constant coefficient is just the value of f at a. The first power coefficient is just the first derivative of f at a. The second power coefficient is f prime of a divided by 2. And the third power coefficient is f triple prime evaluated at a divided by 3 factorial, and so on. So in general, the coefficient of the nth power of x minus a is the nth derivative of f evaluated at a divided by n factorial. And the reason for choosing the coefficients in that way is that it's a very simple way of making sure that this polynomial p has the same value and the same derivatives as the original function f at the point a, right? So in fact, the value of p and its first n derivatives will all have this take the same value as f did, right? Have the same value and the same derivatives at the point a. By the way, I'll ask you as an exercise to actually just work out by hand what are the derivatives of this function. But the way you can verify this fact is that, well, for example, when you take the first derivative, no, I'll tell you what, let's just take the constant value. Suppose you want to evaluate p at the point a. Well, when you plug in x equals a, all of these higher order terms go out. They disappear, right? Because x minus a becomes 0, and therefore all that's left is f of a. So that verifies this fact, right? What happens with the first derivative? Well, if you take the first derivative of p, then the constant term disappears. The first order term loses the x minus a. It'll just become f prime of a. All the higher order terms will lose 1 power, right? The power goes down by 1. But that means when you plug in a for x, all these higher order terms will go to 0 because x minus a will be 0. And therefore, the only thing remaining in f prime when you plug in x equals a will be this, f prime of a, right? And so you can actually just write out the derivatives and convince yourself that, in fact, p of x will have all the same derivatives as f had, at least up to the nth order, and when evaluated at a. Right? Not necessarily when evaluated elsewhere, of course, but at least at the point a, that it'll have the same value and the same first n derivatives. Now, because of that, if we take the difference, f minus p, right, the original function f minus its approximation p, then this error function, which I'll call h, will be 0 at a, and its first n derivatives will also be 0 at a, right, because everything's going to cancel for the original value and the first n derivatives. Therefore, this h is what I've been calling a bootstrapping function, right? Its value and first and derivatives are all 0, and therefore we can apply the previous theorem to it, right, to get an estimate of how big this error is. One other thing to note is that because p is a polynomial of degree n, its n plus first derivative will be 0, and therefore, when you take the n plus first derivative of h, the px will disappear, and the n plus first derivative of h will be exactly the same as the n plus first derivative of f, right? So h and f have the same n plus first derivative. Therefore, when I apply the previous theorem, I can substitute f, the n plus first derivative f, for the n plus first derivative of h, right? So I'm using that here, and therefore I can say that the error is going to be equal to the n plus first derivative of f evaluated at some point c between a and x times the same polynomial, x minus a to the n plus 1 over n plus 1 factorial. Okay. And so Taylor's theorem says that this approximation in the green box is good up to an error of this amount in the pink box here, right? And so it tells you what the approximation is, and it also gives you a very nice expression for what the error will be in that approximation. Right? Now notice that this error term tends to get better as n gets larger. So if you have a function that has a lot of derivatives, then you're going to, and then you use those derivatives to make up a big polynomial like this, you should be able to get a very good approximation, because as the number n gets larger, well, what happens? Let's see, this quantity n plus 1 factorial in the denominator gets larger, so that makes the error smaller. And if you don't move too far away from a, like in particular if you're within 1 unit of a, then this quantity is going to get smaller. Even if you're not that close to a, n plus 1 factorial is going to increase faster than x minus a to the n plus 1 as n gets bigger, right? Because this just increases by a factor of x minus a for each increasing n, whereas this increases by a factor of n plus 1, right, which gets bigger. And so as long as the derivatives don't blow up, right, as long as these higher order derivatives of f don't become catastrophically large, if they remain bounded, then the error is going to approach 0, right? And this is how you can show that, in fact, there'll be an infinite series representation of a function, because if you continue this polynomial approximation infinitely, right, as n goes to infinity, the error goes to 0, and that gives you a power series representation of the function. But we're not going to be concerned with that in this class. We're really going to be concerned with a polynomial approximation of a finite order like this and its error term. And that's what we're going to be focused on. So we're going to be working with this error expression a lot in the future. Okay, now let's do a case study of applying Taylor's theorem to an approximation of a particular function. You probably remember from calculus that for small values of x that are close to 0, sine x is approximately equal to x. And in fact, that is a kind of a Taylor polynomial approximation. So just to verify that, if f of x is equal to sine x, then its derivative is cosine, its second derivative is minus sine, its third derivative is minus cosine. And when you evaluate f and its first two derivatives at 0, you find that the values are 0, 1, and 0. Now you get the same result for the polynomial p of x equals x. If p of x equals x and its first derivative is 1, its second derivative is 0, when you evaluate those three functions at 0, you get the same values, 0, 1, and 0. So this polynomial p of x equals x matches sine x at 0 at the value of the function and the first two derivatives, right? Therefore, the error in this approximation is going to be a degree 3 bootstrapping function, right? So the error in the approximation given by p is going to be the third derivative of f evaluated at some point c between 0 and x, right, which in our case, we're looking at the interval from 0 to pi over 12. So c has got to be in that interval between 0 and pi over 12, divided by 3 factorial times x minus 0 cubed. Notice that in this case, we're taking a to be 0, right? Our base point, our center point is 0. In our case, we saw that the third derivative of x was equal to minus cosine. And of course, this function in absolute value is never bigger than 1. So what we can say is that the third derivative is, that should be the third derivative, not the nth derivative. The third derivative in absolute value is never bigger than 1. So this gives us a nice value for this approximation. We can say that in worst case scenario, the absolute value of the error could be, well, this could be as big as 1, this is 6, and this, the biggest it could be would be pi over 12 cubed. And if you plug all that into the calculator or MATLAB, you find that it's a pretty small error, 0.00299, etc. Now, that's not necessarily an acceptable error, just because it seems to be a small number. Because after all, the values of sine x are also pretty small when x is small. Remember, sine of 0 is 0, so this could still represent a large relative error. So on the next slide, I'll look at estimating the relative error in this case. So let's look at the relative error of the same approximation to sine on the same interval from 0 to pi over 12. Now, we saw that the absolute error was given by that bootstrapping function, so the third derivative of f divided by 6 times x cubed. And in our case, the third derivative was minus cosine, so in absolute value, it's no bigger than 1. So we can say that the absolute value of the absolute error is no greater than 1/6 x cubed. The relative error is simply the absolute error divided by the value of the true value of the function sine x. So I'm going to write this as 1/6 times h of x, where h of x is this function x cubed over sine x. Now we have to do some a little slightly painful analysis of this function. What we want to determine is where does this function reach its maximum, right? That would represent the worst case scenario for the relative error. So where does h hit its maximum? Well, it turns out that h is going to be an increasing function, and so it's going to reach its maximum at pi over 12. But how do we know h is an increasing function? It's not terribly obvious just by looking at it. So we can say, let's take the first derivative of h, we get this. And if you factor the numerator, you see this. Now, x squared is positive, sine squared is positive, so this will be increasing as long as this expression is positive, right? So as long as this expression, 3 times sine x minus x times cosine x, is positive, then h is increasing. Now, as I said, I'm going to claim that h is increasing over this whole interval, so I'm going to claim this is positive over the whole interval. How do we determine that? Well, that's not so obvious either. So let's do it again. Let's take the derivative of this expression. And what we see is that its derivative is equal to this. It's just 2 cosine x plus sine x. Finally, we have something that's easy to interpret. This number is always positive on this interval, right? The interval from 0 to pi over 12. This expression is always positive. So therefore, this function is constantly increasing. And at 0, the value is 0. So this is a function that starts off at 0 and it's constantly increasing. So basically, it's always positive on this interval, right? And since this value is always positive, that means h is always increasing. And therefore, h is going to achieve its maximum at the right endpoint at pi over 12. So plug pi over 12 into MATLAB, to evaluate the function h, and you get, I think I did this correctly, 0.0693. And then remember the relative error was 1/6 of h. So worst case scenario is the relative error is 1/6 of 0.0693, that comes out to be a little over 1%. Okay, that's not bad. On the small interval, 1% relative error. And remember, the error, even the relative error, gets better as you approach 0, right? So not a bad estimate, actually, for narrow intervals like this.